In this episode, we start with key exchange, algorithms, key length, and protocol selection, because these ideas explain how encryption becomes usable in real systems. It is one thing to say that data should be encrypted. It is another thing to understand how two systems agree on a key, what mathematical method protects the data, how strong that protection should be, and which secure communication protocol should be used for the situation. If you are new to cybersecurity, this topic may sound intimidating because it includes terms that feel technical very quickly. Stay with the purpose first. Secure communication needs a way to protect data, a way to choose strong methods, and a way to avoid outdated choices that attackers may already know how to break. You do not need to memorize every mathematical detail. You need to understand the decisions that make cryptography trustworthy or risky. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. Key exchange is the process two systems use to agree on secret key material without simply sending the secret in a way that anyone can copy. This matters because symmetric encryption is fast and useful for protecting a lot of data, but both sides need the same secret key for the protected session. If one system simply sends that secret key across an untrusted network in plain form, an attacker watching the traffic could steal the key and read the protected conversation. Key exchange solves that problem by helping the systems create or agree on shared secret material without exposing the final secret directly. You can think of it as the setup phase before the protected conversation begins. The systems are not just talking securely yet. They are establishing the conditions that will allow secure communication to happen. The important point is that key exchange is about creating trust and secrecy at the beginning of a session. When you connect to a secure website, your device and the server need to agree on how to protect the conversation. They need to use methods both sides support. They need to make sure the server is the right server. They need to create keys that can protect the actual data flowing between them. Public key infrastructure, PKI, and certificates may help prove identity, while key exchange methods help create session keys. A session key is temporary key material used for that particular conversation. This is useful because the systems do not have to rely on one permanent secret for everything. A temporary session key limits exposure and supports safer communication. Some key exchange methods are designed so that even if a long-term private key is later compromised, old session traffic remains protected. This idea is called perfect forward secrecy, PFS. The name sounds absolute, but the basic purpose is practical. You do not want one future key compromised to unlock a large archive of past captured traffic. Attackers may record encrypted traffic today and hope to decrypt it later if they steal the right key. PFS reduces that risk by using temporary key agreement values, so each session has its own protection. If one session key is exposed, it should not automatically expose every other session. This is one reason modern protocol choices matter. It is not enough for a connection to be encrypted. The way keys are established affects how much damage a later compromise can cause. An algorithm is the method or set of rules used to perform a cryptographic function. Encryption algorithms protect confidentiality. Hashing algorithms support integrity by creating a fixed-length value from data. Digital signature algorithms help support identity, integrity, and non-repudiation. Key exchange algorithms help systems agree on shared secret material. When people say an algorithm is strong or weak, they are talking about whether that method can still resist realistic attack with current knowledge and computing power. A strong algorithm has been studied, tested, and accepted by the security community for its intended purpose. A weak algorithm may have known flaws, design problems, or a key size that is too small. You do not need to design algorithms. You need to recognize that choosing an outdated or inappropriate one can weaken the entire security design. Modern security depends on using algorithms that are trusted for the job they are doing. Advanced Encryption Standard, AES, is a common example of a modern symmetric encryption algorithm used to protect data efficiently. Rivest-Shamir-Adleman, RSA, is an older asymmetric algorithm family that has been widely used for encryption and signatures, though its safe use depends on proper key length and modern configuration. Elliptic curve cryptography, ECC, is another asymmetric approach that can provide strong security with smaller key sizes than some older methods. You do not need to compare every algorithm in detail right now. The bigger lesson is that different algorithms solve different problems. One may be used for bulk encryption. Another may help with signatures. Another may help with key exchange. Security weakens when a method is used for the wrong purpose or kept in service after it is no longer considered safe. Key length is one of the factors that affects cryptographic strength. A key is not the same thing as a password, but the general idea of difficulty still helps. A longer cryptographic key usually gives an attacker more possible values to search through, which can make brute force guessing much harder. Brute force means trying many possible keys until the right one is found. But key length is not the whole story. A long key used with a broken algorithm may still be unsafe. A strong algorithm used with a poor implementation may still fail. A key stored in an exposed location may be stolen without anyone needing to break the math. So key length matters, but it must be considered with the algorithm, implementation, storage, lifecycle, and protocol being used. Strong cryptography is a system of choices, not one number. You may see different key lengths for symmetric and asymmetric algorithms, and they should not be compared as if they mean the same thing. A symmetric key of a certain length does not provide the same kind of strength as an asymmetric key of the same length. Asymmetric methods often need much larger key sizes to reach a comparable security level, depending on the algorithm. This is why you might hear about AES using key lengths that sound much smaller than our SA key lengths. That does not mean AES is weaker by default. It means the mathematical systems are different. You should avoid judging strength by size alone unless you know which algorithm family is being discussed. On the exam, pay attention to context. The safe answer often depends on whether the question is about symmetric encryption, asymmetric encryption, hashing, signatures, or key exchange. Outdated cryptography creates risk because attackers do not need to defeat the strongest possible protection if a system still accepts weak options. A protocol or algorithm that was once common may become unsafe as research improves, computing power increases, or practical attacks are discovered. Weak hash algorithms can allow collisions, where two different inputs produce the same hash value. Weak encryption algorithms may be vulnerable to known attacks or too small a key space. Old protocol versions may have design flaws or support insecure negotiation. This is why secure configuration often includes disabling older algorithms and protocols. Keeping weak options enabled for compatibility may help an old system connect, but it can also give attackers a weaker path. The question is not whether the system supports encryption in general. The question is whether it supports strong encryption and refuses unsafe choices. Protocol selection is about choosing the right secure communication method for the situation. A protocol is a set of rules that systems follow so they can communicate. Transport layer security, TLS, is commonly used to protect web traffic and many other application connections. Secure shell, SSH, is used for secure remote administration and file transfer purposes. Internet protocol security, IP security, can protect network traffic at the network layer and is often associated with virtual private network, VPN, designs. Each protocol was created for particular kinds of communication and has its own strengths, assumptions, and configuration choices. You do not want to choose a protocol just because it sounds secure. You want to match the protocol to the use case and make sure modern versions and safe settings are used. TLS is a useful example because it brings several ideas together. It can use certificates to help verify server identity. It can use key exchange to establish session keys. It can use symmetric encryption to protect the data after the session is established. It can use integrity protections to help detect tampering. But TLS can be configured well or badly. A modern version with strong algorithms and proper certificate validation can provide strong protection. An outdated version with weak cipher options may create unnecessary risk. A certificate warning may indicate that trust could not be validated properly. A misconfigured server may support older methods that should have been disabled. When you see TLS in a scenario, do not stop at the word encrypted. Think about identity, key exchange, algorithm strength, certificate validation, and protocol version. Protocol selection also depends on what you are protecting. Web applications commonly use TLS because the goal is to secure communication between clients and servers at the application layer. Administrative access may use SSH because it is designed to protect remote management sessions when configured properly. Site-to-site connectivity may use IP security because the organization wants to protect traffic between networks. Email may use different security mechanisms depending on whether the goal is protecting transport, signing messages, or encrypting message content. The purpose should drive the choice. If the scenario is about protecting a website, the answer may be different from a scenario about protecting a remote administrator session or a network tunnel. Security is stronger when the protocol fits the communication pattern. Backward compatibility is one reason weak protocols and algorithms remain in real environments. An organization may keep an old system because it supports a critical business process. That system may not support modern encryption settings. To keep it working, people may allow older protocols, shorter keys, or weaker algorithms. This can create a difficult trade-off. If you remove the weak option, the old system may stop working. If you keep the weak option, the environment may remain exposed. Good security decisions try to reduce this risk rather than ignore it. That might mean upgrading the system, isolating it, limiting who can reach it, monitoring it closely, or using compensating controls until it can be replaced. You should hear compatibility as a warning sign. It often explains why risky choices remain, but it does not make them safe. Key management is part of this topic because strong algorithms and protocols still depend on protecting keys through their life cycle. Keys need to be generated securely, stored safely, used only for the right purpose, rotated when appropriate, revoked or replaced when compromised, and retired when no longer needed. A system using a strong protocol can still be weak if the private key is copied into unsafe locations or if the same key is reused for too many purposes. A strong database encryption method can still fail if every administrator can access the key without oversight. A signed update process can still be abused if the signing key is stolen. When you evaluate cryptographic security, do not look only at the algorithm name. Look at how the keys are handled and how trust is maintained over time. You should also understand that protocol negotiation can become a risk when weak options are allowed. During a connection setup, systems may need to agree on which version, algorithm, or cipher suite to use. A cipher suite is a named combination of cryptographic choices used for a secure session. If both sides support strong options, negotiation can lead to a secure result. If one side still allows weak options, an attacker may try to force or trick the connection into using something weaker. This is why administrators disable old protocols and weak cipher suites instead of simply hoping modern options will be chosen. A secure system should not offer unsafe choices just for convenience. The safest configuration reduces the number of weak paths available to attackers. For exam scenarios, focus on the risk described rather than getting lost in technical names. If two systems need to agree on a secret without exposing it, think about key exchange. If a question asks why old encrypted connections are still at risk, think about outdated protocols, weak algorithms, or poor negotiation choices. If the question mentions a key that is too short, think about brute force resistance and modern strength requirements. If the question mentions protecting web traffic, TLS may be relevant. If it mentions secure remote administration, SSH may be relevant. If it mentions protected network tunnels, IP security or VPN concepts may be relevant. Always ask what is being protected, where the communication occurs, how trust is established, and whether the selected method is still considered strong. The conclusion is that cryptographic security depends on more than simply saying the word encryption. Key exchange determines how systems safely establish secret key material. Algorithms determine the mathematical method used for encryption, hashing, signing, or key agreement. Key length affects resistance to brute force attacks, but it only makes sense in the context of the algorithm and how the key is protected. Protocol selection determines which communication rules are used for the situation, and weak or outdated protocols can create serious risk even when encryption appears to be present. As you continue studying, keep the purpose clear. You want strong modern methods, safe key exchange, appropriate key lengths, proper validation, and protocols that fit the job. When any of those pieces is weak, the trust built on top of them becomes weaker too.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.